Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 14, Linear and Exponential Models, Comparing Growth Rates. Classwork Example 1, Linear Functions. Sketch point P1 equals the point 0, 4. Okay, so I brought in a coordinate plane here, and I will sketch P1 as the point over 0 up 4, which is right here. So that is P1. And P2 is 4, 12. So here's 4, and all the way up here is 12. So it's right here. There's P2. Are there values of m, the slope or rate of change, and b, the y-intercept, such that the graph of the linear function described by f of x equals mx plus b contains both points 1 and 2? If so, find those values. If not, explain why they do not exist. Okay, so for starters, this is the y-intercept. So if I have the equation y equals mx plus b, and my y-intercept is 4, I already know that my equation starting out with y equals mx plus 4. Okay, so that would give me this point right here. No matter what the slope is, as long as that is 4, it will plot this point here, because no matter what m is, when x is 0, anything times 0 is 0. 0 plus 4 is 4, and that'll give us this value. But now we also have the graph that contains the point 4, 12. So if I take my equation right here with my b, and I know that y is 12, I don't know my slope. I know my x is 4, right? 4 is x, y is 12, plus my b, then I can find m by subtracting 4. And 12 minus 4 is 8, equals m times 4, or 4m. And these cancel. I divide by 4, and this cancels, and I'm left with m equals 8 divided by 4, which is 2. So now I have the equation y equals 2x plus b, which was 4. So y equals 2x plus 4 is my equation. So then if I graph that, it would look like this, but it would continue in both directions forever. So I would have arrows here, like so. So there is the line y equals 2x plus 4, going through the point 0, 4 and the point 4, 12. So in answering this question, are there values of m and b such that the graph described contains these points? The answer is yes. And m, as I stated here, m equals 2, and my b equaled 4. So those are the two values we were looking for to make this true. Okay, part b. Now we have the point 0, 4 and 0, negative 2. Are there values of m and b so that the graph of the linear function described by f of x equals mx plus b contains point 1 and 2? And if so this is point 1, this is point 2, find those values. If not, explain why they do not exist. Okay, so here we go. So sketch the point 0, 4. So 0, 4 is right here. And the point 0, negative 2, which is right here, right on the edge of my graph, over 0, down 2. So there are my 2 points, 0, 4 and 0, negative 2. So this should create a line that goes through those 2 points. Let me extend it further this time. Okay, so there it is. And then if I draw arrows on the ends, so there's what my graph should look like. So just graphing those 2 points, then I should understand that yes, there should be an m and a b, so that there's a graph of All right, so anyway, we write y equals mx plus b. We know that b is, when x is 4, or when x is 0, y is our b. So b equals 4. So now I have y equals mx plus 4. So we know b equals 4. We were given it. Anytime x is 0, y is our b. But now we have 0, negative 2. So we also have b equals, so then if I did this again, I would say, well, y equals mx minus 2. Actually, that should be blue. Okay, so b equals negative 2. Uh-oh. So what's going on here? All right, so I need to find an m. So if y equals mx plus 4 and y equals mx minus 2, then mx minus 2 must equal mx plus 4 by the transitive property, right? If a equals b and b equals c, then a equals c. So then I'd have mx plus 4 equals mx minus 2. So if I subtract mx from both sides, then those go away, and I get 4 equals mx minus mx is 0, and I get minus 2. Well, obviously, 4 does not equal negative 2, so m does not exist. Okay, when we have a vertical line, slope is undefined. The other reason for this is we have an x mapped onto two different y's. And when that happens, we do not have a function. Okay, page 2. Exponential functions. Graph C and D are both graphs of exponential function of the form g of x equals a times b to the x. Rewrite the function g of x using the values for a and b that are required for the graph shown to be a graph of g. Okay, so keep in mind that our y-intercept is a. And our exponent, our base, I should say, is the value that will give us what we need to make this function true on at these points. So if I write g of x equals a times b to the x, and I know a is the y-intercept, the y-intercept is 0, 2, so the y-intercept is 2, so now I have g of x equals 2 times b to the x. So if I pick a value like negative 2 comma 0.5, 0.5 is my g of x. So I'm going to put that here. Okay. Negative 2 is my x. So that's going to be times some b to the power of negative 2. And I need to find my b. So this will be 0.5. Actually, I need to divide. Let me erase that. I need to divide both sides by 2. So then these cancel. And I get b to the negative 2. And how about I change that to 1 over b squared because I don't like a negative exponent. And that's the rule. B to the negative 2 equals 1 over b to the positive 2. That was from 8th grade, or maybe even 7th. And so 1/2 divided by 2 is 0.25, or a quarter. And let's change that to a fraction. Okay, so now I have a 1 equal to a 1. So this tells me that b squared has to equal 4. And when I take the square root of both sides, then b equals 2. So my equation is going to be g of x equals 2 to the x. Okay, part D. Again, I brought the reminder down. A in the equation, g of x equals a times b to the x. The a is our y-intercept. Our y-intercept is right here. So that is halfway between 2 and 4, so that is 3. So our a equals 3 here. So now we have g of x equals 3 times some b to the power of x. And then I pick one of these 2 points. I'd rather avoid the fraction. I'll use the -1 as my x and the 2 as my y. So my g of x or my y. So 2 is g of x equals my y-intercept times some b to the power of my x, which is -1. So I'm going to divide both sides by 3. These cancel. And I'm going to rewrite b to the -1 as 1 over b equals, that's b to the +1, equals 2/3. Okay? So, in order to get b out of the denominator, I have to multiply both sides by b over 1, if you will. And if I do that, I get 2/3 b equals 1. And then to get the 2/3 out of there, I have to multiply both sides by 3/2. So 2 cancels a 2, 3 cancels a 3, or you could think of it as 3 times 2 is 6 over 6, which is 1b. So b equals 1 times 3/2, or simply 3/2. So now my equation is g of x equals my a, which was 3, times my b, which is 3/2, to the -1. Actually, I don't want to put the -1. It's an equation in general, so this should be x. Did I do this up above here? No, I did put the x. Okay. So this is a general formula. G of x equals 3 times 3/2 x. So now if I put 2 in here, I want to check, see if this is true. So I want to see if 27 over 4 is truly equal to 3 times 3/2 to the power of x, which is 2. So 27 over 4 equals, well, 3/2 squared is, 3 squared is 9, 2 squared is 4. Okay. So then 9 times 3 is 27. So this 27 over 4 equals 9 times 3, which is 27 over 4. So that is true. So my answer is right here. I just checked to see if this was also true. Never hurts to check. Example 2. A lab researcher records the growth of the population of a yeast colony and finds that the population doubles every hour. So hours in study, yeast colony population in thousands. Complete the researcher's table of data. Okay, so doubles every hour. So we start with 5. It doubles after 1 hour. It doubles after 1 hour. So we're just doubling this, multiplying by 2. 20 times 2, 40 times 2. And there's the table for our data. Okay, page 3. I've brought the table over so I don't have to keep flipping back and forth. Part B says, what's the exponential function that models the growth of the colony of the population? So I'm going to first start out by writing f of x equals a times b to the x. There's our exponential function in general. Okay, f of x is a function that we name. It's often good to use letters that make sense in the context of the problem. We're talking about yeast colony population. So we could call that population with respect to time, hours in the study, P of t. So P of t is our function where t is time. Okay, so remember, A equals our y-intercept. And our y-intercept is 0, comma what? And these are our x's, or our, I should say, in this case, our t's. So since it's P of t, these are our t's time, and these are our P of t's down here, are our y's. So we have the point 0, comma 5. So our A is 5. So I already know that P of t is 5 times some base to the power of t. Okay, so now I take any other value, substitute it in to find our b, because we have a P of t and we have a t. So it doesn't matter which one we use, it should be true for all of these. So why not pick an easy one like 1 and 10? So P of t is 10 equals 5 times some base to the power of t, which is 1. Okay, well, b of 1 is simply b, so that equals 10. So that means 10 equals 5b. So when I divide by 5 on both sides, I'm kind of out of room here, but I'm sure you can see that dividing by 5 will get us b equals 2. And therefore, P of t equals A times b to the t. And then we can always check our solutions. So if I put a 4 in here, 2 times 2 is 4 times 2 is 8 times 2 is 16. 16 times 5 is 80. And we have 80 here. So that checks. Part C says, several hours into the study, the researcher looks at the data and wishes there were more frequent measurements. Knowing that the colony doubles every hour, how can the researcher determine the population in half-hour increments? Explain. Okay. So let x represent the factor by which the population grows in a half an hour. Since the population grows by the same factor in the next half hour, also t, the population, will grow by t squared in 1 hour. However, the colony's population doubles every hour. So in other words, if it doubles every hour, so if t equals 1, we're multiplying 5 by 2. If t equals 2, we're multiplying 5 by 4. So that hour, it doubled. It went from 2 to 4. So t, or actually squaring the 2. 2 doubled is also the same as 2 squared. So if t squared equals 2, our time squared, our doubled time, right? 3 squared is 3 times 3. 3 doubled is 6. 3 squared is 9. So that doesn't work. Okay, so think of it as this. If the factor is going to change from 0 to the first half hour, and we're going to call that change x, okay? That makes sense? We don't know how much it changes, but from 0 to a half hour is a change of x, and then it goes to the next half hour. Well, this is a constant rate of change, so that's going to be another x. So it doubles. So if we multiply those, we get x squared. And since we have a factor of x squared, and we know we're multiplying it by 2, then x squared equals 2. And if we take the square root of both sides, the square root of x squared is x, and therefore x equals a factor of the square root of 2. Part D. Complete the new table that includes half-hour increments. So here it is. Now we want to complete the table. Well, we already know that 1 is 10, and 2 is 20, and 3 is 80, or 40. Okay, I got that from the table up here. Doubling every hour. So I already know those are 10, 20, 40. All right, but what I need to find is this value here. So 5, how do I get this value here? Well, it's this factor right here. If x equals the square root of 2, and we're taking a half an hour, that's a factor of square root of 2. We're going to multiply by the square root of 2. So let me explain it with a calculator. So if I multiply this by a square root of 2, and then multiply this answer by a square root of 2 again, what's a square root of 2 times a square root of 2? Well, that's 2, and 5 times 2 is 10. So half of these multiples of 2 are multiples of the square root of 2, if that makes sense to you now. Hopefully that makes more sense to you now. So the answer to this is 7.071. It's not half of 10, which would be, or halfway between 5 and 10, which would be 7.5. It's not quite that. Okay, but then if I multiply 5 times 0.7071, I get 5 times square root of 2, I get 7.071. Now if I multiply 5 by the square root of 2 times the square root of 2, which is 2, I get 10. So to get this one, I have to multiply by multiples of 3 square root 2, and I'd have to multiply these by 4 square root 2's. Okay, square root of 2 times the square root of 2 4 times. Let's think of it that way. So let me get this out of here. All right, so this is the square root of 2. This is the square root of 2 times the square root of 2, which is 2. This is the square root of 2 times the square root of 2 times the square root of 2, which is the square root of 2 cubed. And this is the square root of 2 times the square root of 2 times the square root of 2 4 times. So let me just write this out. I'm just trying to explain this so it's less confusing. We're multiplying by factors of the square root of 2 to get this, and then another square root of 2 to get this, because the square root of 2 times the square root of 2 is the square root of 4, which is 2. Well, square root of 2 times the square root of 2 is 2, and the square root of 2 times the square root of 2 is 2, and 2 times 2 is 4. Another way I could have done that is 2 times 2 is 4, times 2 is 8, times 2 is 16, and the square root of 16 is 4, and therefore 5 times 4 is 20. Okay? So now we're going to take 3 halves, and we're taking 5 and multiplying it by the square root of 2 to the 3rd power. So I can say 5 square root of 2, move outside, and cube that. And hit enter. And I get 14.142. And then this would be 2 to the 4th, square root of 2 to the 4th. This is square root of 2 to the 5th, and this would be square root of 2 to the 6th. Okay? So now I go to my calculator, and I do 5 square root 2 to the 4th, and hit enter, and I got 20. And then I do 5 square root 2 to the 5th, and I get 28.284. Okay, and then just to verify this, I'm going to do the last one. 5 square root 2 to the power of 6. Whoops. And I get 40. Okay, so there we have it. Hopefully that wasn't too confusing, or if it was, hopefully I cleared it up. E, how would the calculation for the data change for time increments of 20 minutes? Explain. Okay, so you can think of it this way. If I go back up to here and say x squared equals 2, okay, we're doubling every factor of x squared because there are 2 half hours in 60 minutes, right? 2 30-minute blocks in 60 minutes. How many 20-minute blocks are in 60 minutes? 20, 40, 60. There's 3. So we would just change our exponent to how many of this size blocks are in the hour. So now I'd have x cubed equals 2, which is doubling. And then if I solve this, I take the square root, or I'm sorry, the cube root of x cubed. I want to solve for x. So if I take the cube root of one side, why am I writing cubed? So if I take the cube root of x cubed equals the cubed root of 2, the cubed root of x cubed, they cancel each other out, and I'm just left with x equals the cube root of 2. So the researcher could multiply the population by the cube root of 2 every 20 minutes. Complete the new table that includes 20-minute increments. So I get my calculator. Let's just clear that. And 0 was 5. 1/3, that's one 20-minute block. I'm going to multiply 5 times the cube root of 2. So it's 5 times and I have to hit math first, and number 4 gives me cube roots. So 5 times the cube root of 2 is 6.2999 or 6.3. Let's round that to tenths. Okay? And then I'm going to take 5 times the cube root, math 4, the cube root of 2, and that's going to be 2 of them. So do I square that? And I get 7.937. Okay, and then 1, I already know is 10, but I'm going to check it by using my formula here. Okay, that 2 should be outside, but since it was 2, it doesn't matter. But I'll be careful next time. 5 times math 4 for the cube root of 2, get outside of here, and now I'm going to change this to cubed and hit enter. And obviously the cube root, oh, it puts it inside after, so it is 10. So see how it matches with 1? 10. And then I keep going. So now I'm going to take 5 times math 4 for cube root of 2, and then I'm going to do to the power of 4. Enter. And I get 12.599. Or you could say 12.6, I suppose. Okay, 12.599. And then 5/3, or an hour and 40 minutes, would be 5 math 4 to get my cube root of 2. And I want this to the 5th power. And I hit enter, and I get 15.874. And 2 should be 20, but I'll check it with my calculator. 5 times math 4 for cube root, 2 to the power of 6. Okay, that is my 6th 20-minute increment, which is 2 hours. Hit enter, and I got 20. It matches here. Okay, page 4, part G. The researcher's lab assistant studies the data recorded and makes the following claim. Since the population doubles in 1 hour, then half of that growth happens in the first half hour, and the other half of that growth happens in the second half hour. We should be able to find the population at t equals 1/2 by taking the average of the population at t equals 0 and t equals 1. Is the assistant's reasoning correct? Compare this strategy to your work in parts C and E. So if I go back and look at C, and E. And I look at my tables D and F, well, shouldn't this be 7.5, 10, 15, 20, 30, 40? Isn't 30 the average of 20 and 40? 20 plus 40 is 60, divided by 2 is 30. Is that 30? 10 plus 20 is 30, divided by 2 is 15. Is that 15? 5 plus 10 is 15, divided by 2 is 7.5. Is this 7.5? Okay, so obviously that is not what we should be doing. The assistant's reasoning is not correct. By the assistant's reasoning, the population growth at the first half hour would be t 1/2, which is 7.5, which I've just stated, because then the population would have grown by 2.5 thousand cells from the 5,000 cells in the first half hour, and another 2.5 thousand cells to 10,000 cells in the second half hour. This is a linear growth, or the same amount of population growth in each half hour. However, the percent growth by the assistant's reasoning is 50% from t equals 0 to t equals 1, and 33% from t equals 0 to t equals 1. So for the population to double in 1 hour, there must be constant percent growth in each half hour. Example 3. A California population projection engineer in 1920 was tasked with finding a model that predicts the state's population growth. He modeled the population growth as a function of time t years since 1990. Census data shows that the population in 1900 in thousands was 1,490. In 1920, the population of the state of California was 3,554,000. He decided to explore both a linear and an exponential model. A says to use the data provided to determine the equation of the linear function that models the population growth from 1900 to 1920. Okay, so we are taking a function with respect to time and its population. So I'm going to use P of t, population, P of t, or y equals m times x, or t in this case, plus b. Okay, it's linear. B is what? Time 0, which is 1900. The population in 1900 in thousands was 1,490 in thousands. Okay? So that is the point, 1900, comma, 1490. But it says that we want the time to be t years since 1990. See it right there? So if it's 1900, t years since 1900 is 0. If you're in 1900, how many years is 1900 from 1900? 0. And that's 0, comma, 1,490. Thousands. Okay, 1,490. That's pretty messy. So there's our y-intercept. There's our b. So now I have P of t equals some rate of change times time plus 1,490. Remember, this is in thousands. Can't write a 9 today for some reason. So it's 1,490 in thousands. And then I have another point from the year 1920. Well, how many years is 1920 from 1900? It's 20. So that is the point 20, comma, and our population then is 3,554 thousands. So it's 3,554. Okay, so there's my t, and there is my P of t. So I put 20 in for t. Okay, my 20 is my P of, or my t, and my P of t, is 3,554. So I'm going to first subtract 1,490 from both sides. And that is going to get me 20m equals, I just flipped it around, 20m equals 4 minus 0 is 4. Okay, 15 minus 9 is 6. That's now a 4 minus 4 is 0, and 3 minus 1 is 2. Divide both sides by 20, and I get m equals, well, if I divide it by 2, that'd be 1032, and then dividing it by 20 moves the decimal over one place. So my m is 103.2. So now my function, now I'm going to take my function and plug in what I have found. So my p of t equals mx plus b, 103, or mt plus b. All right, so 103.2t plus my b, which was 1490. So there's the equation of my line. Okay, so I don't want to call this p of t at the same time because they're two different functions. So population growth, I'll call this g of t. So what they're asking us to do here is use the data provided and your calculator to determine the equation of the exponential function that models the population growth. So I'm going to call it g for growth over time equals, and remember, if it's exponential, then it's sum a times b to the t. All right, remember our a is our y-intercept, so now I know g of t equals our y-intercept, 1490, times sum b to the t. So all we need to find is b because I have a t and I have a g of t, and we're going to use these two values right here. So g of t is 3554 equals 1490 times b to the power of 20, our t. I'm going to divide both sides by 1490. These cancel, and I get b to the power of 20 equals, and I want to be able to read my screen, the calculator's in the way, 3,554 divided by 1490. And I get 2.385. Okay, so in order to find out, this is a little bit too complex to do with, we'd have to do logarithms to find exponential values, to find a base. What to the 20th power equals this? Okay, so I'm not going to explain that to you. You could use trial and error, and you could say, what is 2 to the power of 20? Okay, and I'm looking for this. Okay, so I do know that it's g of t equals our a, 1490, times some value to the power of t. Okay, so I just did 2 to the 20 and got this really big number. Well, I want it to be 2.385, and this is 1,048,576, 2 to the 20. So if I take 1 to the 20th power, 1 is less than 2, so I'm going to go reduce it. 1 to any power is 1. So now I know that this number is between 1 and 2. Well, is it 1.1 to the power of 20. Okay, we're getting closer. See how I have 2.385? Now I'm down to 6.72. So 1.1 was too big. How about 1.05 to the 20th? Now I'm down to 2.65, getting closer, see? Okay, so 2.65 is more than 2.38, but I'm getting closer, so I know it's 1.0 something. So now I'm going to try 1.04 to the power of 20. And I got 2.19. That's not enough. So now I know it's 1.04 something. So 1.04, let's just go halfway this time, to the power of 20 equals 2.41. That's too much. So how about 1.044? Let's come down by 100th to the 20th. And I get 2.365, 2.38. So I'm getting close. So let's just be, so it's 1.044 something to the power of 20. And as you can see, I'm getting closer and closer and closer to what I'm looking for, which is 2.385. I have 2.388 right now. So I know it's 1.044 something. So we're getting closer, but let's just put 1.044 in here. There is a way to calculate that, and they're called logarithms. You won't see those until Algebra 2. Okay, so there's our equation that we are looking for using our calculator and trial and error. Okay, here we are on page 5, part C. Use the two functions to predict the population for the following years. So we have the two functions. Let me bring them in. Okay, so here are our two equations. This one's linear, and this one's exponential. Now notice I named this P of t because it was population with respect to time, and this was growth with respect to time. And notice that they've called these F of t and G of t. So to avoid confusion, I will just change this to an F. So F of t is my linear, and G of t is my exponential function. All right, I'm going to save some time in doing this now, and I'm going to put these in my calculator under y equals. So I go to y equals, and I plug in 103.2 and x plus 1. Okay, 103.2, x is my t, plus 1. Enter. So there's my linear function. And then I'm going to put 1490, parentheses, 1.044, close the parentheses, to the power of x. Okay, so if I graph these, probably won't see anything here. I'd have to hit zoom 0 to fit it because the values are so huge. Okay, zoom 0. Maybe it won't do it. There we go. There's our linear function, and there's our exponential growth going up, and that will be curving. It's hard to see, but you see it's curving. It's going to shoot up faster. Not interested in the graphs at this moment. What I want to do is go to my table. And the next thing I want to do is calculate values that they're asking for here. So the year is 1935. Remember that it's years since 1900. So my x in this case, or my t, is 35. 1935 minus 1900 is 35. 1960 minus 1900 is 60. And 2010 minus 1900 is 110 years. So these are my values I care about in my table to find these numbers. So I'm going to plug in 35, 60, and 110 for x in my calculator. So to do that, I go to my table set, I switch it to ask, and then I hit second graph to go to a table. And I plug in my x's. Let me just move this over here. I want 35. I want 60. And I want 110. So there are my three values, 35, 60, and 110. That's these three here. And y is 3,613 linearly. Okay, I made a mistake here. It's not plus 1, it's plus 1490. So did I do that in my calculator? Y equals, yes, 1490 second graph. My apologies. Okay, so 35 years, population is 5,102. After 60 years, 7682. And after 110 years, 12,842. Going over to the table for my y2's is my exponential growth. I have 6725. Don't worry about the 0.2. It's an approximation anyway. This 0.44 is rounded. And then 19734. And then finally, 169919. Okay. So there are our values from our equations that we came up with. D says, which function is a better model for the population growth of California in 1935 and in 1960? So, which is closer? 51 is almost 1,000 away. 67 is less than 600 away. So, exponential's better for 35. 60, this one is 7,600. This is 15,000. That's only half. This is only 4,000 off. So for the first two, the exponential's better. Okay, so which function is better modeled? The exponential model is better for the first two. Part E says, does either model closely predict the population for 2010? So the population for 2010 was 37,253,000 people, where this is 12,000, so that's like a third. And this is 169,000, which is like 4 times, okay, greater. So this is only a third, and that's 4 times greater. So I'd say neither model is a good representation when we start getting into larger values. Okay, so neither model closely predicts the population. After a population boom from 1900 to 1960, the population growth slowed down. The following graph shows census and intercensal estimates for California's population between 1900 and 2010. Intercensal. Okay. Times between censuses, I guess. Alrighty. And there's the graph. So it started to take off exponentially, but then it slowed. Because if it was continuing exponential, what it would do is it'd come up like this, and it would continue growing exponentially this way. But it slowed and turned out to be almost linear. So it started exponential and then turned almost into a linear function, if you will. So it slowed down. Okay, page 6 brings us to the end of lesson 14. Review this lesson summary and go do your problem set.